The final talk this afternoon is given by Dario Tamascelli from Milano. He will be talking about simulating spin-boson models, trapped ions, a non-perturbative approach.
So hello everybody. First of all, thanks to the organizer for giving me the opportunity of presenting this work here and for this very nice conference, and also for having fixed the weather, which seems to be getting better. Now, what I'm going to talk about today is something which is open quantum systems. So suppose you have a very complex quantum systems and that you can't access to the full complexity of these and actually are not so interested in simulating or know every feature of this quantum system, but you're actually interested only in a subsystem of these. So open quantum system approach does the following. So this part of the system, your open system, and you treat the other remaining many degrees of freedom as the environment. Now, the goal of open quantum system theory is to describe the reduced dynamics of the system, which is defined as the trace over the environmental degrees of freedom of the overall density matrix, in such a way to essentially determine all the expectation values of this subsystem. Now, the final goal of this talk is to show you that actually we can use the beautiful platforms that have been discussed widely during this conference to simulate open quantum systems, and I will refer in particular to trapped ions implementation of the scheme that I'm going to discuss. Now, the starting point of my story with open quantum system is the following. Now, in nature, there are many systems that harvest light, the energy from the light, to gain the energy to proceed with chemical reactions and so on. Now, there are some of these systems, such as green sulfur bacteria, live in very low light conditions, and for them, it is vital to exploit, to use every single photon that comes. Now, it turns out that these are very complex systems. Part of this system is the Fehn-Matthews-Olsen complex, and it has very remarkably efficiency of transferring one excitation from the injection point, so where the light gets actually the surface of the bacteria while the light gets caught, to the reaction center where the subsequent chemical reaction happens. Now, this efficiency stimulated quite a few some research, and people start wondering whether, you know, there are quantum walks. They seem to give you some speed up in transfer of an excitation from one point to another of a graph. So whether quantum coherences were playing any role in this process. Now, surprisingly enough, this is a biological system, wet conditions, hot conditions. It seems so there were experiments that show that actually coherences were present at room temperature in such complexes. Now the question is still open and widely debated, and I don't want to enter into that. But this is an example of a very complex open quantum system. So just to make the scheme simple, you have these pigments here. They are connected. They are interacting with a quite well-known Hamiltonian. But each of them is surrounded by an environment, and most importantly, the interaction with this environment is not weak. So you cannot try to simulate that by using simple Markovian approximations, lambda dynamics, and so on. And you have to figure out something more elaborated. Now, I was really fascinated by this problem. I am a computer scientist by training, And I said, okay, how people do this kind of things. Actually, it turned out that even simulating this single component of the FMO complex is already quite complicated, and that was really the starting point of this. Now, before moving on, I want to mention the people that collaborated on this project and actually are still collaborating on this project. So I was working in the group of Martin Pleño at that time and still collaborating with them. And so we have Andreas Lemmer, Tobias Schetz. This guy here is Andreas Mirne. Just keep him in mind. He will appear later on in another form. Cecilia Cormick, actually in Cordoba, and Susanna Huelga. Now, outline of my talk, I will just tell you very briefly what the spin-boson model is, how usually people simulate it, and then I will move on toward the main topic of this talk, which is just look for some equivalent but simpler system and how to simulate that on trapped ions. So spin-boson model. Each pigment in the FMO complex is ultimately a two-level system, and it is surrounded by a local environment that is this cloud. Now, this local environment can be modeled as a very large collection of independent modes, each interacting with the system with, let's say, an Hamiltonian term, which is transverse in the free with respect to the free Hamiltonian of the system. Now, this model is archetypal for open quantum systems and can be modeled very simply. Okay, so this is the overall Hamiltonian, so free Hamiltonian of the system, free Hamiltonian of the environment, interaction Hamiltonian, where you see this transverse Z here. So it's not a pure dephasing dynamics. Now, usually the number of modes is very high, so you can pass to the continuum, and after very trivial things, you end up with what is known as the polyphase Hamiltonian. And in this Hamiltonian here, what plays a central role is this guy here, which is the spectral density, which somehow tells you how much the system interacts with every single mode. Now, how you simulate that? So we have a system, very simple two-level system, and then we have a huge amount of normal modes, actually a continuum. Now, there is one way to do that, is not the only way, is to perform a unitary mapping of these infinitely many modes into other modes. The advantage of this mapping is that now these modes are arranged in the nearest neighbor configuration with XY, with, what's that? Beam splitter, so exchange Hamiltonian. And to simulate that, you can exploit very efficient techniques such as TBD, which is a version of time-dependent density matrix normalization group. So interesting. So this is a method that belongs to a wider family of methods. So the reaction center coordinates is efficient in the sense that it scales polynomially with the system plus chain size, and is certified. I mean, you can evaluate estimate the error at every step. Now, this, by the way, this was used to prove some interesting physics. Now, let's move to the simulation in a physical setup. Not too many years ago, Porras and other people proposed a way to simulate an open quantum system by using a mesoscopic, that is to say, a system made up of many, many ions in an ion trap setup. Now, this is a very well-established technology, and we heard amazing things during this conference. But the question is, but still, we have, in order to simulate a fully fledged spectral density, we need many of these bosons. Now, can we do things simply, in a simpler way? The answer is maybe yes. So let's start from this very nice observation. It's a particular case, but I will tell you something more toward the end of the talk about the generalization of that. So if you consider, so your system is here, then you have your environment, which is made up of one single mode, which is then interacting with a secondary bath, which has what's called an ohmic spectral density. Now, it was old result, 83 from Garg, Onucic, and Ambegaukar, that the effective spectral density as experienced by the system is actually an anti-symmetrized Lorentzian, which has this formula here. And perfect. Now, I was talking about the spectral density. Obviously, consider the Hamiltonian. If we know the spectral density, we know everything about the system. But now, let's focus a little bit on how the spectral density really determines the dynamics of the reduced system. Now, it's easy. I mean, just leave alone the technicalities. But what you have to study is the time evolution in Heisenberg representation of the interaction operator that appears in the interaction Hamiltonian. Now, if you study that, then you can say that that's the 2 times correlation. You can study the 2 times correlation function, and by taking the Fourier transform of that, you end up with what's known as the correlation spectrum. Now, the correlation spectrum is actually something that depends on the initial state of the system, but is really given once you know the spectral density. Now, from now on, I will talk about the correlation spectrum and as the spectral density. I mean, they are one-to-one related. So, simpler system. What do I mean? Lindblad type. Instead of using this one, I remember you, it's made up of many independent modes, and you have to simulate all of them, in principle. Let's see what happens if instead of that, I take one single damped harmonic oscillator. Now, the dynamics of the new environment is governed by a Lindblad master equation. And if you, in general, the two things are not equal, but there is quite a wide parameter regime where they are very, very, very close. And in the following, so this is for an example for this particular choice of the parameters. And in the following, I will focus on 3 examples. So one, when the, let's say, when I have the system that is very far away from the resonance frequency of the environment, and other cases where we have a resonant interaction. And I will show you that this system has interesting features. Now there is a theoretical problem. The Polyphirth Hamiltonian is bilinear, so everything here is linear. And on the one side, we have a given spectral density, and on the other side, I have another environment which undergoes a Lindblad dynamics. Now, suppose that the spectral density here is equal to the spectral density here. I should talk about 2 times correlation functions, but they are related. So, is it guaranteed that the, sorry, oh, yes, okay, that if the 2 spectral densities are equal, the reduced dynamics of the system is the same? Now, if you think about linear response theory in the classical domain, you will say yes. I mean, it's obvious. But the first thing that you learn when you start studying quantum mechanics is there is nothing obvious, actually. So we had strong numerical evidence that it was indeed the case, but there was someone, the guy appearing before, that was not satisfied at all with that. And actually, we went looking for a proof of this fact. And after some reasoned argument and some catalysts, we ended up with answer, and the answer was yes. So the proof of this equivalence is very easy, but I don't want to bother you with this. I mean, it's just the hypotheses are important, so we only require the system to be, the initial state system environment to be factorized, and we require the environment to be initially in a Gaussian state. So the theorem says that as long as the first and second moments of the interaction operators appearing in the Lindblad picture and in the unitary picture are the same, then the reduced dynamics of the system, when attached to the Lindbladian environment, let's say, and to the unitary one, are exactly the same. And the proof is really technical, but it's easy, and passes through a unitary dilation of the Lindblad part. So applications where there are quite a few, but let's look at the results. So these are plots. In every single plot here, you have the dynamics as determined by the original unitary dynamics with T-DOPA and TDMRG, and then what you get with Lindbladian dynamics. Now, you can't tell the difference. Okay, here you have what happens when you have this ohmic regime. You are sampling the spectral, the frequency of your system is far away from the resonance frequency, and you have an underdamped, damped, and overdamped regime, depending on the interaction strength with the environment. And here you have what happens if you are close to the resonance. And you can see there is a non-trivial dynamics here, and actually you can quantify the degree of non-Markovianity of the dynamics by using different non-Markovianity measures, such as the Breuer lane pillow or the Huelga-Pleño and Rivas-Huelga-Pleño measures. Interesting point, at least computationally, is that the T-DOPA techniques took up to 6 weeks to give the results, which is not a huge amount of times. We were using only 16 cores on our cluster in Ulm, whereas the Lindblad simulation were performed in 12 seconds on my PC, so which is something interesting, I think. And the accuracy of the results, it was strikingly good. Now, back to simulations with trapped ions, just to close the story. Original scheme from Porras and Zirac and others, and new scheme now. What we are looking at is, so we take an ion crystal, you encode the two-level system in the nuclear spins of one of the ions, and then you use one of the two vibrational normal modes of these ions to encode the harmonic oscillator. Now you can couple the two-level system to the out-of-phase vibrational mode by using two laser beams, and then you can drive the transitions here in the two-level system by using other lasers. And the damping that you have on the harmonic oscillator, which is the mode here, can be obtained by sympathetic cooling and on these ion here. And by choosing two different ionic species, you have, so you make it so that this sympathetic cooling doesn't spoil the interaction between the two and doesn't spoil the dynamics of the two-level system. Okay, so yeah, that's more in detail. I mean, all the details of this, including a detailed discussion of the effect of the coherence and other experimental problems are discussed in the paper. And let me go to the conclusion. So we were able, somehow, non-perturbatively, to replace a unitary environment with very good approximation with a Lindblad type environment. The agreement, as long as the reduced dynamics of the system is concerned, is strikingly good. And while doing this, we bumped on quite interesting theoretical results. And by using this scheme, you can really try to use trapped ion setup, but I think you can even also use cold atoms. I'm not an expert in this, to simulate the evolution of a not so easy open quantum system with a very simple, I would say, setup with respect to what I saw here in the previous days. But that's not all. I mean, so I was talking about a particular spectral density, this antisymmetrized Lorentzian spectral density, but actually what we are aiming at is a box where you feed in the spectral density that you need, and in output, you get a linear combination of, a suitable linear combination of simpler damp modes that do the job for you. I mean, in the sense that the resulting spectral density in the two cases are very close to each other. And that would go through what we like to call lindlets, so analogous to wavelets. And to extend it, the class of spectral density can be easily, to at least find out what class of spectral density can be easily decomposed. And OK, and I think that's only a first step toward the simulation of maybe not all, but at least a bit something more of interesting open quantum systems such as the FMO complex, and that's all.
Thank you very much. Open for questions, comments. Yes, please.
Just a brief question. In the sympathetic cooling scheme that you do you have an estimation of the time scales needed for cool down the dark ion in this scheme?
Well, so let's say that, so I don't have any idea about the times required, but the experts on that were Andreas Lemmer and Tobias Schetz, and they checked everything carefully, so it's perfectly accessible. I mean, it's something that, so. Okay, yeah, thank you. So, sorry for being able to give you the answer.
So I'm very interested in this open quantum system type of research. So I wanted to ask, how many modes do you have to damp to? So what is the complexity, basically, in shaping your desired spectral density to get some realistic, model of, for example, this seven spin model of this molecule? So have you explored this direction and try to understand how the complexity scales when you want to simulate something more realistic?
Well, let's start from the single two-level system. So right now, the number of DEM modes that you need depends strongly on the spectral density that you want to simulate. So for example, our numerical experience tells us that you need maybe 2 or 3 modes for a super ohmic spectral density, whereas you need something more, I don't know why, for the ohmic spectral density. But that's an open problem. We are working hard on that. I mean, we want to really find an efficient procedure and automatic. So really this box where you say, OK, I give you the spectral density, just tell me. Now, we don't have these available yet, but our experience says that on the average, if you are lucky enough, you can do the job with 5 or 4 damped harmonic oscillators that maybe are connected to each other, so they are not independent damped modes. So that's the point. I mean, maybe you need to have harmonic oscillator that are each one damped, but then they are interacting, just to give you more structure on the spectral density.
Any further final? Yes?
As far as I know, you have to do the Markovian approximation if you derive a Lindblad master equation. How does this work together with your results that you get some non-Markovianity in your reduced system?
Well, there is not. So if you had the system that is itself governed by, so alone and governed by a Lindblad master equation, you will be perfectly right. But in this case, you have a mode that interacts with your system, and the mode is then. So you have more structure there. Okay. So the dynamics is non-Markovian. Why? Because you have your system, which is attached to an environment which is all but flat in spectrum. I mean, it's different structure. So and that passes through, you know, you have to extend, I mean, you have to take an oscillator or many oscillators, depends on what you want to do, as to enrich the structure of the environment. Otherwise, if you have only the Limblad master equation for the evolution of your system alone without additional modes, you wouldn't have anything but the Markovian dynamics.
The full dynamics and the Markovian, and basically the Limblad easy model.
If you have many oscillators?
Yeah, if you have many damped oscillators, because you showed the correspondence between one damped oscillator and basically the Limblad description, right?
Yeah, no, that
and
corresponds.
if you have many damped oscillators, this correspondence still holds, at least numerically.
Okay, so once you have found this auxiliary system, which will undergo by itself Limblad dynamics, that gives you exactly the same 2 times correlation function as the original unitary environment, then you are done. If it is equal, then you have really an equality of the reduced dynamics. If there you have some approximation, and we are actually convinced that you cannot have equality, actually, then there will be something different, but there is another result that I stupidly forgot to mention here, which sets quite tight bounds on the, the discrepancies that you have in the system, so the reduced system observables if you change a bit. I mean, if you perturb the spectral density. So I hope I will tell you more about that in a couple of maybe months, maybe 6, because they're working hard on that.
Okay, thanks for a nice talk and a very good discussion. So I would like to finish this day's lectures and talks, and thank you all speakers of today. Thank you, and